let's start with 11.6 and 11.6. 11.6 and 11.7 is the last two sections we have, and it's all deal with this normal distribution. So in the sense, the idea of this normal distribution is this, ladies and gentlemen, is ideally if you have the ideally if you have the data, whatever data that you try to collect, ideally the mean, the median, and the mode will at the same location. And it's very hard, but it will be at the one location, and which is at the center of this location here. And this center, which is will be your mean. And this bell-shaped curve will be symmetric. We will have 50% of the data below the mean, and we will have 50% of the data above the mean. Okay. So one thing is we probably, realistically, we won't get there. But in the sense that the idea of this item is basically tell you that if you collect a lot of data, if you select a lot of data and a lot of data, eventually it will be this symmetric. So if you think in terms of the coin I asked you earlier, or if I did not ask you, let's say if I ask you, if I have a fair coin, if I have a fair quarter, and I flip the quarter and I ask you, what is the chances, what is the probability of me flip the quarter and the quarter land on a tail? You will say, well, the quarter, you have two-sided, right? And one side of the tail out of two sides, which is 50%. So for one time I flip the quarter, I will have 50% of land on either a tail or a head. But if I ask you, if I flip the coin 10 times, does it guarantee that I have 5 head and 5 tail? You would say you might have 5 head, 5 tail, but it does not guarantee, right? It might be 7 head, 3 tail. If I flip 100 times, I might have 60 head, 40 tail. If I flip 1,000 times, I might have 550 head, 450 tail. Meaning, basically, if you flip this quarter a lot of times, let's say if you flip this quarter 1,000,000 times, then it will trend to that theoretical probability in terms of 50-50. So the same idea with that quarter is this sample that you have is basically tell you that if you collect a lot of data, your data will eventually become a bell-shaped curve or symmetric. Okay. And the unique thing about this bell-shaped curve or symmetric is the area underneath this bell-shaped curve is 1. And the area underneath this bell-shaped curve is the same as the probability of some item that we have. Okay. So our goal is we want to know what is the percentage of the data between this item, or what is the area between this item. Okay. So if we look at this bell-shaped curve, for instance, let's say that we have this bell-shaped curve, and they give you this thing here, the height, the data is the height of the adult of the woman. The graph below show the normal distribution of the height of the woman in the United States. The number in the horizontal axis is the height in inches, and the area are labeled as follow. So they ask you, what is the mean height? If you look at this bell-shaped curve, what will be the mean height of this item? If you remember in the previous definition, the mean, the median, and the mode is at one location. And hopefully you guys see that in the middle, the highest peak of your bell-shaped curve, which is the middle of this bell-shaped curve, is your mean. And in this case, the mean, you can see that the mean height for this woman in the United States is 63.7 inches. Okay, so whatever the mean is, that's what they have. And this is what they ask you is, what is the percentage of women between the height of 57.4 and 59.1 inch high, tall. So the percentage is the same as the area. One thing, ladies and gentlemen, make this note or make this item right here is if they ask you for the percentage, if they ask you for the area, if they ask you for the probability later on, they will ask you for probability. All three of the item is the same thing. The percentage, the area, and the probability, all three of them is the same thing. It's just the different terminology, but they ask you for the same item. So if we're looking at this thing here, if they ask you what is the percentage of women between the height of 57.4 and 59.1 inch tall, the percentage will be 3.4%. Again, if this is a decimal, you convert to percentage, which is you move the decimal place 2 places, and the percentage will be 3.4%. If they ask you for the area, it would be 0.034. If they ask you for probability, it would be 0.034. Again, if they ask you percentage, we just need to convert the decimal to the percent, and to make the decimal to percentage, you move the decimal 2 places to the right. So in this case, you have 3.4%. Okay, and if they ask you if there are 2,000 women in the stadium for the concert, how many of them would be expected between the height of 63.7 and 66.0, right? So if you look at this thing here, how do we find the number of people? To find the number of people, all you do is you take the percentage, or in this case, you take the area multiplied to the total people you have. So if we have 50%, let's say if we have 50% and there are 2,000, meaning again, 1,000 will be this much, right? In this case, they tell you that you have 30.3%. If 30.3%, which is how many people we should expect? 606 people, 606 women will be between that height. What we do is we take the area, we take the number, multiply to the total. So for this particular bell-shaped curve, for this particular normal distribution curve, they give you the percentage. They give you the percent, they give you the area. You just need to extract them out, right? And if they say if we have 1,000, how many would we expect to be between the height of 57 and 59? If we have 1,000, we should expect, again, 3.4 of the person, which is roughly 4 people, right? Basically, we take this thing here, time 1,000, you have 3.4, and if we time 1,000, well, actually 1,000 will be 34. So again, if we have 1,000, there will be 34 of them. 34 of them will be between this height. If it's 1,000, right? 1,000 times this number will give you 34. Right. So again, looking at this thing here, question of how to find the percentage or how to identify given this table. For this particular problem, yes, they will give you the percentage. In the next one, they won't. But because this thing here, because it's symmetric, there is a small rule that they will give you, which we will see. For this thing here, if they ask you to identify like this, then they will give you the area and the percentage. What if they don't, right? Someone asked, will they always give it to you? Well, if they don't, this is what your idea, or this is what you guys need to do. So before we do this item, or before we mention about the other table that we have, let's take a look at the empirical rule. So for any standard normal bell-shaped curve, for any bell-shaped curve, this is what you have, is we have this empirical rule. Because we know it's symmetric. And again, if you take this number, ladies and gentlemen, if you take this number, this number, this number, and this number, if you take this number that I highlighted, if you add them all together, it should be equal to 50%. What does that mean? That means that if we have this bell-shaped curve, there are 50% of the data below the average. This is the mean, this is the average. There are 50% of the data below the average, and there are 50% of the data above the average. Okay, this is what the empirical rule tell you. That, and again, in the sense, this is what the idea of this percentage is. Think about this table, or not table, think about this bell-shaped curve. At this item, do you agree that if we're looking for the area, if we're looking for the area underneath the curve, this is the highest peak I have. And the higher the peak, as you can see, the bigger the area, right? The lower the peak, the smaller the area I have, because the curve is slow, the area is less and less and less when we deduct or kind of decrease the region, the height of this item, right? So the majority of the data, or the majority of the percentage, is right here. The majority of the percentage, as you can see, is right here at this location. This is where the highest peak, and this is where the majority of the data. Okay, so the empirical rule come in. All this thing here lead us to this empirical rule. The empirical rule come in is this. They tell you that within one standard deviation, meaning the mean, if you take one step above, and you take one step below, it will consider 68% of your data. We forget about the decimal here, forget about the 0.1 for now. The empirical rule, we just guesstimate, we go up to the next whole number. So for this empirical rule, don't worry about this decimal. For the empirical rule, this is what they tell you is, if we from the middle, if we take one step above, meaning one step to the left, one step to the right above, and one step to the left, if we take one step above and one step below, it will include 68% of my data. Meaning, if I have 100 people, let's just put 100 people in total. If we have 100 people, 68 of them will be surrounded, will be cluttered around the area, the mean. Okay, so the empirical rule tells us that if we go up one, down one, it will be included, or will be considered 68% of your data. The second item is, if you go up two, if you take one step above, or two step above and two step below, it will consider 95% of your data. Okay, so again, the second rule is, if you go up two and go down two, it will consider 95% of your data. And lastly, the empirical rule tells us that if you go up three and down three, if you go up three and down three, this thing will consider 99.7% of your data. And again, up one, down one, 68%. Up two, down two, 95%. Up three, down three, it will include 99.7% of your data. Meaning the area underneath the curve will be that. Okay, and that's what the empirical rule tell you, that for any bell-shaped curve, that's what you will have. You will have 68% of the data within one standard deviation. You will have 95% of the data within two standard deviation, and you will have 99.7% of the data within three standard deviation. The word within basically tell you walk up two and walk down two, or walk up three, walk down three. Okay, that's what the word within mean, meaning you have to go above and you have to go below. And again, the symbolic that you see that the X is the mean, which is the average, and the standard deviation, which is the S. 1 meaning 1 time S, 2, and so on. So looking at this thing here, looking at this item, and again, let's take a look at this particular problem. Let's say that they ask you this. Let's say that they ask you this item, and most of the question they will ask you something like this, and they want you to use your empirical rule to identify this problem. So the intelligence test, the IQ, is normally distributed. And again, the only reason why they say normally distributed is basically they tell you that it's a bell-shaped curve. With the mean IQ is 100 and the standard deviation is 15. If 40,000 people taking the test, how many would you expect to have an IQ between 70 and 130? So before we see how many people we should expect, let me ask you this question. How many people score between 70 and 130? Okay, so don't, that's the question they ask you is, if we have the mean of 100 and the standard deviation of 15, how many people, or what is the percentage, or what is the area underneath the curve between 70 and 130? So if you look at this question here, do you agree that they give us this item here? They give us this item in terms of the mean and the standard deviation. Okay, and if you remember the mean and the standard deviation in the previous problem, this is what we have is the mean is 100, which is in the center. Okay, for now, don't worry about this number here. For now, don't worry about this numbers here. Let me ask you this question. Do you agree that this is based on our previous chart, the mean, which is in the middle, and the middle tell you that 100, and if I take one step above, this is the idea of the empirical rule, ladies and gentlemen. If you take one step, you add 15, which is the standard deviation, which is the S. And if you add 15, do you agree that 100 add 15 will give you 115? If you take another step above, you add another 15. And if you add another 15, that will give you 130. If you take one step below, meaning you go to the left, you need to minus. And if you minus 100 minus 15 to give you 85. And if you take one step below, you take 85 minus 15 to give you 70. So again, why do I do in this item here? Because do you agree that this is what they asked me? They asked me between these two value, 70 and 130. Between these two value, 70 and 130, what is the percentage? So let me ask you, how many steps did you take above and how many steps did you take it below? Do you agree that you take 2 steps above and 2 steps below? And if you take 2 steps above and 2 steps below, if you remember, your empirical rule is 95% of your data is within 2 standard deviation. And again, within 2 standard deviation is basically how many steps did you take. If we take 2 steps within 2 standard deviation, meaning you take 2 steps above to the right, you take 2 steps below, which is to the left. And again, this is the number we're looking for. We're looking for the percentage of the data between 70 and 130. And what is that? How did I get to 70 or how did I get to 130? How many steps do I take? Each step I take, this is the unit that I need to deduct or this is the unit that I need to add. Okay, and if you look at this thing here, let's go back to this. Give me 1 second here. Let's go back to this item. If you look at this slide, right? If you look at this thing here, if you say, wait a minute, Mr. Tran, this item and the previous item that I saw, number 1, number 2, number 3 is not the same, because this thing here, they tell you that this is your X bar, which is your mean. And if you relate to the previous problem, your mean is 100. And what is your S? Your S is 15, right? Do you agree that in the previous problem, our mean, which is the mean is 100, and the S, the sample standard deviation, is 15. So if you plug in the S where you see the S, and the S is right here, right? If you plug in the X bar and if you plug in the X bar, which is 100 minus 2 times 15, what is 2 times 15? 2 times 15 is 30. Again, if you plug into our item, we have X bar is equal to 100, and our S is equal to 15. And if you plug into this formula, X bar minus 2S, which is X bar is 100 minus 2, what is my S? My S is 15. Do you agree that 100 minus 30 and 100 minus 30 is 70? So this thing here is basically the genetic formula or genetic item that you have. And in the sense, this is what we have, right? And similarly, on this side, we have X bar plus 2S. And again, what is X bar? X bar is 100 plus 2 times that, and 100 plus 30 is equal to 130, right? So in the sense, that's where the two number, or if you were to see this thing here and you say, you don't see why we have 70 on this side and 130 on this side, is basically we plug into this formula. Okay, this is the formula we have, which is X bar minus 1S, X bar minus 2S, X bar minus 3S. Same thing on the right, add 1X, add 2X, add 3S. Okay, so looking at this item, and again, the S is basically tell you, or the number 1, number 2, number 3, basically tell you how many steps you need to take. Okay, and in this case, I took, like I say, I took 2 steps. I add, instead of add 15, 15, that's where I add 30, right? Instead of minus 15, I minus 30. So that's where everybody see that is where I identify the two number I have between 70 and 130. And because I took 2 steps, within 2 steps, I have 95% of my data. And that's not answer the question. The question, they did not ask you what percentage. The question they ask you is, how many people would we expect, right? So to do this thing here, you need to convert your decimal, your percentage to the decimal, and multiply to the total number of people we have. So we should expect 38,000 people out of 100 or 40,000. Out of 40,000, we should expect 38,000 people between this score. So again, if we give this test to 40,000, we expect 38 of them will score between 70 to 130. We don't know the actual score, but we expect that 30,000 of them, 95% of them, which is 38,000, will score between that two number. Okay. So again, looking at this thing here, let's take a look at another problem. I know some of you guys are a little bit puzzled. Let's take a look at another problem, and then hopefully the second time around, hopefully you will see the a little bit easier. The given data is normally distributed with the mean and the standard deviation, and the n, which is number. Find the approximate number for the data value for in the given range. So let's say that this is what they give us, is they give us the X, which is the mean is 400. The standard deviation is 2025. Reminder, the standard deviation here is the S, right? And they give you the N, which is the total sample that we have. Now they ask you, how many out of this 500 people, how many should you expect to fall under the range of 325 and 475? Okay, so basically you ask yourself, well, from 400, which is the middle, how did I get to 325, or how did I get to 475? Okay, how much different is that? So if you look at this thing here, the 400 is in the middle, right? And if I go up one, I need to add how many? If I go up one, I need to add 25. So again, if I go up one, I add 25. Is that the value I'm looking for? Hopefully you say no, because I'm looking for 475. If I'm going up that one, I need to subtract, which in this case, 375. That's not the range I'm looking at. If I go up one more, I add 25. If I go down, I subtract. And finally, if I go up, I add 25. If I go down, everybody see that every time we go up one step, we need to add this much unit. Again, imagine if me and you, if you taller than me, if you take one step, you will travel, let's say, if you take one step, you will travel, let's say, 18 inch. And for me, if I take one step, I travel only 7 inch, right? So it's depend on the data, right? You say, wait a minute, Mr. Tran, the previous problem, when I go up one, I add only 15. Why is this problem when I go up one, I add 25? Well, this data is different from the previous data, right? Just imagine if you walk or you run faster, right? Let's say in an hour, I run 2 miles, not that much, but let's say in an hour, I run 2 miles, and in an hour, you run 3 miles. Then it depends on a person, right? So it's depend on the data. This one here, because the data they give me is 25, so every time I move one space, I add 25, compared to the other one is only 15. Every time you move one space, you only add 15. Okay, so go back to this item here. They ask you, and again, the reason I give you this thing here, because I think some of the question on your Alex, they give you this kind of question, is they give you, again, they give you this item here. They ask you, in this range, 325 and 475, 325 and 475. How much do we expect? How many people out of this 500 should we expect between this range? So you have to connect this to your empirical rule, and your empirical rule tell you that if you go up 3 steps, and if you go down, it have to be up 3, down 3. If you go up 3, down 3, that will include 99.7. right? If not, you can take each of this percentage and add them together. You can take 2.2 plus 13.6 plus 34.1. If you take those, add them together, is close to this number here. Okay, it's probably 98. 99.8 instead of 99.7. But again, if you take this number, this is what they tell you is within 3 standard deviation is 99.7. And how do we find how many people out of 500? Well, we take the percentage multiplied to the total. So 99.7 convert to decimal will be 0.997 times this, and we will say that we have 499 people. Because of the number of people, we cannot take half of the person. So because of the people, we round up to the whole number. Okay. So looking at this thing here, I don't think so. If you put 99, because 99.8 and 99.9, when you multiply, you will get somewhere, you will get in the sense that if you use, because they ask you for the number, this thing here, they don't ask you for the percentage. If you put 99.998 times 500, you still get 499, right? So if you were to use for, because the question up here, they ask you how many people would you take, and someone asked if they use 99.8%, will that be wrong? Well, 99.8%, you take 99.8 multiplied to 500, and if you do that, you have 499 people. So the answer is still the same. So because they ask you how many number, right? Approximate the number of people, the number of data. So again, you still get the same answer if you use 90, unless Alex asks you for the percentage. And if you put 99.8, might be they tell you it's wrong. But again, this one here, because they ask you for the number of people, no matter how many decimal, you always go up to next location. Okay. So again, same idea go. If you were to have this thing here and they were to ask you, let me ask you, the question is, what if they ask you how many people, how many data are between 375 and 425. If they ask you this question, everybody see that again, between these two number, 375 and 425, everybody see that within one standard deviation, which is 68%. So if you were to do this item, all you do is you say, well, we know that within two standard deviation, that is within one standard deviation, they are 68%, right? And to do this thing here, you just say 68 multiply to 500, which is the total people we have, and 0.65 multiplied to 500, you will see that you have equal to 340, meaning again, there are roughly 340 people or 340 data out of this 500 data that we have will be between this number, between 375 and 420. Okay, so again, if you make this number, if you make this table, is easy to look at. And one thing about chapter 11.6 and 11.7, this is what I advise you guys to do. Sketch your normal distribution curve. Sketch this bell-shaped curve. It take you like, it doesn't have to be precise. It's just give you an idea of how many steps do we need to take. It's give you an idea of what is the area we're looking for. Sketch it and then graph it. Okay. So one thing about the empirical rule, one biggest thing about empirical rule, and some of you already asked, some of you probably say, what if they don't ask you 1, 2, and 3? What if they trick you and they want just this much? They want half of it, right? They want half of instead of go the whole one step. What if I want half a step? What if I want a half a step on back and half a step in the front? We cannot just divide 34 by 2 because the height of the graph up here is bigger or higher than the height of the graph down here. So they are not that equally the same, right? So there is a small limitation with the empirical rule. And the empirical rule, one thing about the empirical rule is they can only jump one step above, one step below, 2 step above, 2 step below, 3 step above, 3 step below. We cannot calculate half of the step. We cannot jump 1.5 above and 1.5 step below, right? What if I want this, right? What if I say I want the percentage between -1 and 1.5? How would we do that, right? How do I find this percentage? How would I go and find the area underneath the curve between -1 and then 1.5, right? So there's no combination for empirical rule for you to do that. No, there's nothing you can do because we don't know, we cannot justify that this much data is the same as this much data when the height are different. As you can see, the height are different, right? We cannot just take 13.6 divided by 2 and call it a day because this one here have more than this one here, right? So that leads us to this thing here, ladies and gentlemen. This leads us to become a z-score. So z-score, the z-score is basically you try to, the z-score is a standard normal. And the standard normal is, in short, the standard normal is basically tell you that if you have, doesn't matter what the data is, doesn't matter how fast you run, how slow you run, how wide your step is, how small, narrow your step is, doesn't matter if the height, the weight, whatever you try to collect. If you can convert that to a standard normal, if you can convert whatever your data to this bell-shaped curve, then the bell-shaped curve will have the same distribution. They will be the same item all the time. So as long as it's in this bell-shaped curve, which is the normal distribution, that's what the bell-shaped curve is. It's a normal distribution curve. If as long as it's a bell-shaped curve, we will have the same structure all the time. Doesn't matter the height, doesn't matter the weight, we will have the same structure. So the first thing we need to do is we need to convert your data to the z-score. And when you convert your data to the z-score, it tells you this item. It tells you how far away are you from the mean. If you have a positive z-score, then you're above the mean and you know how far above you are from the mean. If you have a negative z-score, you will be below the mean and you will know how far away from the mean you are based on your z-score. Okay. And again, this is the two items I mentioned. If you have a negative z-score, you are below the average. If you have a positive z-score, you are above the average. So how do we find a z-score? Right? How do we find a z-score? And this is probably the last thing we have in terms of the formula. This is the z-score we have. Is we take the data, this item right here. This item is your data minus the mean divided by the standard deviation. Take the data minus the mean divided by standard deviation. Okay. So one good thing about statistics, ladies and gentlemen, and when whoever take 2 or 3, the good thing about statistics is everything that they ask you to do, there is a formula that you can do or the formula that you need to plug in. And the bad thing about statistics is, ladies and gentlemen, everything they ask you will have formula. You have to know which formula to use for your problem. You need to know what formula that you need to use and what item to plug in so that you can find the item that they ask you. Okay. So one thing is, let's look at this problem here. They will ask you find the z-score. So find the z-score is good. That's what we're looking for. We're looking for the z-score. And to find the z-score, this is what we need. We need the z-score. So this is what we need to looking for. We need to looking for my data, my mean, and my standard deviation. So this is what they ask you is, given the SAT score is normally distributed with the mean of 1,498 and the standard deviation of 347. Find a z-score for a student who score 1792. So looking at this item, do you agree that they give us the data? They give us the mean and they give us the standard deviation. They give us the data, which the data is what is the score for that particular student. That is your actual data. They give us the mean, 1498. They give us the standard deviation, 347. So they give us everything we needed, right? They give us the mean, they give us the data, they give us the standard deviation. Do you agree that all we need to do is plug in the formula? And if we plug in the formula, the z-score here is 0.85. And we can see that 0.85, we can see that 0.85 is positive. And if it's positive, we see that this student is above the mean. And you can clearly see this right here. You can see that the average is only 1498, and this student scored 1792, which is way above or is higher than the average. And if it's higher than the average, as you can see, is above, which this item will give me positive. Okay, so let's take a look at another one, right? Let's take a look at another one, and let's say, and this is the unique thing about the z-score, ladies and gentlemen. This is the unique thing about the z-score is, as like I mentioned, doesn't matter the height, doesn't matter the weight, doesn't matter how fast you run, how slow or stuff. If you can convert to the z-score, you can compare your data, right? So for instance, imagine that this is the question they ask you is the university, if whoever tried to apply to Xavier, and then for you took the ACT and you scored 30. For me, I took the SAT and I scored 2150. And we both applied to Xavier, right? And then Xavier administrator say, well, who have a better grade? Because the ACT score system is different from the SAT score system. How do I know which student have a better grade, right? We cannot compare the ACT to SAT. If you compare, all SAT is humongously higher than the ACT because it's 2150 and the other one is only 30. But we know that for ACT, there's only 36 is the maximum, right? So looking at this thing here, how do we know which student have a better score? So to know which student have a better score, the first thing you need to do is you need to convert the z-score for the ACT student, and you need to convert the z-score for the SAT student. So do you agree? Let's take a look at the ACT, the SAT first. Do you agree that SAT, the average for the SAT is this? We know that the data for the SAT is 2150. The mean for the SAT is 1498, which is the same mean as before. And the standard deviation is 347, which is the same as we have in terms of this previous problem here, right? So if I convert this, you can see that this student, ACT, the z-score for the SAT is 1.88. Meaning he above or she or the student above the average 1.88. Now, if you construct or if you convert the ACT or find the z-score for the ACT, this is what we have is we have the mean is 21. The standard deviation is 5. And again, score is 30. And again, 30 minus 21 divided by 5. You can see that for the ACT, the z-score is only 1.80. So because the z-score is higher for the SAT, because the z-score is higher than the SAT, meaning this student compared to an SAT student, this guy have a higher grade, right? So the z-score is basically the standard score for everything. The bigger the z-score, the bigger the positive, I should say, the better the corresponding position. Remember, we're looking for the position, right? And the bigger the negative, meaning the worse the position because you are below the average. Okay, so in this case, there's no way you can compare apple to orange. So what do we do if we want to compare apple to orange? Well, we need to convert the apple to become a z-score of the apple, and the orange become a z-score of the orange, and then we just compare the z-score among themselves. Okay, so again, this is why, you know, people say, oh, you cannot compare apple to orange. Well, now you can say, yes, we could. If I convert to the z-score for both of them, then I compare, right? So again, there's no way we can compare from ACT compared to the SAT because the score system are different among the two. But if we have the average and the standard deviation of the ACT, the average and the standard deviation of SAT, we can compare by change it to the z-score. And if the higher the z-score, the better the grade. The bigger the z-score, the bigger the positive of the z-score, the better grade, because the bigger the negative, the worse the grade. Okay, so in this case, if they were to, if Xavier were to pick one candidate or one applicant, then they will, they will take the SAT student, and because the SAT based on the grade is have a better grade, right? I cannot say smarter because we don't know, right? So, well, first of all, question of how to convert your data to find the z-score. If they ask you find the z-score, this is the formula you need to plug in. Okay. And let's take a look at this thing here. And this is the last item that you will see, or that we will have, ladies and gentlemen. Someone asked me earlier, or if you remember earlier, I told you that the empirical rule is very restricted. And how restricted is the empirical rule? The empirical rule is basically tell you that you have to walk one step above, one step below. You have to walk two steps above, two steps below, so on and so forth, right? And 1, 2, and 3, that's all you can do. But what happens if I want to walk from -1 to 1.5? So here come the standard normal distribution table. And I believe this is the table that you will see on your final exam. I believe this is the table that you will have on your final exam. And this, what is this table say? Well, someone come out and did this, and they tell you that if we have a z-score, and the z-score is the standard number underneath the bell-shaped curve. If we have a z-score, we can find the area to the left. Okay, one thing I want to point out, that this is the z-score. When you look at this item, you have 4 different columns. This right here is your z-score, and the area that they give you, the corresponding area, is the area to the left of the z-score. What does that mean? That means if I were to ask you to find the area, let's say if I have a z-score of 0.85, my z-score is 0.85, and I ask you to find the area to the left of 0.85, meaning I'm looking for this area right here, ladies and gentlemen. I'm looking for the area from this region to 0.85. How do we find this area underneath the curve, or how do we find the percentage, or later on, how do we find the probability? Well, to find the area to the left, life is very easy. Why or how easy? All you do is you're looking for 0.85. In this case, your z-score is 0.85. And then whatever the area that they give you, that is the area to the left of the z-score. So the area or the percentage that they give you or they ask you is this item here. So again, this is my z-score, 0.85. The area will be 0.8023. Or if they ask you find the percentage will be 80.23%. We just move the decimal 2 places. Okay, so this table will be presented to you on the final exam or on your test. You will see this item here, and all you do is you ask yourself, what area am I looking for? Okay, and the challenge is we will see the challenge in a bit, but looking at this thing here, everybody see that this table, what is the information presented to you in this table? They give you the z-score, and they don't give you all of them, right? They don't give you 0.07, right? If you look at this thing here, you say, well, Mr. Tran, what if they ask you for 0.07? They won't. Whatever they ask you will be in this table, okay? So again, if they ask you for the area to the left of negative 0.75, you will say, well, the area to the left is 0.2266, okay? So this thing here, reminder, make a small note for yourself, is whatever this area is, the area to the left of the given z, the corresponding z, the area to the left, the area to the left, the area to the left. So this is your corresponding z, the area to the left of the z. So let's take a look at this thing here, ladies and gentlemen. Let's see if I type it up. Nope, I did not type it up. Let's take a look at this item. Remember your empirical rule. Let's go back and say, let's say, for those of you who say, man, the empirical rule 68, 95, 99.7, I don't get it, I don't see it. Let's say if you don't see it, and let's say if they ask you this question, the problem come in is, let's say if they ask you, let's see if I have any space. If they ask you this question right here, what is the area under the curve is or between z-score of -1 and z-score of 1. So let's say if they ask you this question, that's good, all right? Let's say if they ask you this question here, what is the area underneath the curve or between the z-score of -1 and the z-score of 1? So the challenge come in is you say, wait a minute, Mr. Tran, wait a minute. I know the area to the left, right? I know the area to the left, but I don't know the area in between. So if you look at this question here, do you agree that the z-score of -1 is right here? The z-score of -1 is right there. So let's say that the -1 is let's say the -1 is this much. And the z-score tell me that the percentage to the left, this percentage is 0.1587. Everybody still with me here? Again, this is my z-score. Z equal to -1. And z equal to -1 tell me that 0.1587, which is the area to the left of that. Okay. So now if the area to the left is 0.1587, and let's say, where's my one item? My one item is right here. My z-score of 1 is right here, and the z-score of 1, let me use green. My z-score of one item, let's take a look at, let's say that my one item is somewhere here. And the z-score of the one item, they tell me that the area to the left of this z-score, the area to the left of this z-score is 0.1587. 0.8413. And let me block this thing out so that you won't get confused. And let's say that my z-score z equal to 1, right? So everybody see that the green item is from here, from the left-hand side, all the way to 1 is equal to this item right here, is equal to this number that I have, 0.81, 0.81, not 81, 0.8413. Right, those are my green box. My green box is 0.8413. And my red box, not the original red box, but this is my item here. My red box is this item. Now, if I know from here to here is 0.1587, and I know the green box, which is longer, bigger, 0.8413, how do I find the item in between? Because they asked me for in between. So do you see that in order for me to find an item in between, do you agree that all I need to do is I take the longer value, which is 0.8. Let me change this to black. I need to take the 0.8413 minus the shorter value, which is 0.1587. And if you take this 0.8413 minus 0.1587, if you type this in your calculator, if you take this item, do you agree that it will give you 68 or 0.6827, right? If you take this and you subtract, this thing can give you 0.6827. And this, ladies and gentlemen, 0.6827 is the exact value. And if you remember your empirical rule, the empirical rule, they don't, they don't want the exact value. They just say we guesstimate. And within one standard deviation is 68%. And this is the idea, or this is where we have the 68%. And again, it's basically this item here. We're just using this table to find the item in between, okay? And we will do more of this item here in a bit. But again, that's the idea of this table, is they give you the area to the left. And the problem comes is they only give you the area to the left. If they ask you something as I asked you right here, we have to do some manipulation, okay? But let me ask you, first of all, let me ask you, do you have question of this table here? What is this table represent? Again, the z-score and the area to the left. Make it big store, the area to the left. Now, let's take a look at this thing here. Let's take a look at this item here later. Do I have? Okay. So let's take a look at this item. Let's go back and let's practice some more. And let's say that again, we have this table, and this is what they ask you to do. This is what I ask you to do is find the area under the standard normal curve this for the z-score of 1.2. So if you look at this thing here, and here come, I will cover this and I will let you guys go after this item here, that there are 3 questions that they can ask you relate to this normal distribution table. The first item that they will ask you is they will ask you to find the area to the left of the given z-score. So in this case, and this is what I want you guys to do, this is what I want to advise you guys to do, is first, you want to sketch your normal curve. Sketch your normal curve so that you have an idea of what side of the curve I'm looking for. If I'm looking for the area to the left, which in this case, they asked me to find the area to the left, then life is easy. How easy is this? all we need to do is find the z of 1.2 in your table. In this case, 1.2 is right here. And whatever the area is, that is your area. That is your answer. The area is 0.8849. Then that is your answer. That's your area. If they ask you for the percentage, you convert to the percentage. It depends on your question. They ask you for the percent or the area. Okay. So anything area to the left, anything when they ask you for the area to the left, life is good, life is easy because the answer is from the table. Whatever the table value, that's what they ask you, right? So if they ask you for below or above, it's the same. I mean, not the same. They ask you for below or above. If it's above, meaning the area to the right. And if it's an area to the right, we have to do a little bit different, okay? But again, let's take a look at this example here. And before we do the above, if they ask you for area to the left, do you agree that this is what we have? This is negative 0.2, negative 0.45. The area to the left will be 0.236. That's all we need to do is we find the z-score, and whatever the corresponding z-score is, that is the area to the left. Okay, so area to the left is easy. How easy? We just look at the table, and that's what we have. Now, the complication or the obstacle we have is, what about the area to the right? How do we find the area to the right or above? So if we have this thing here, this is what you need to do is, whatever the area they ask you, whatever the area or whatever the z-score they give you, to find the area to the right, you need to take that area minus from 1. Meaning, if you look at this item, do you agree that they ask you to find the area to the right of z-score equal to 1.7? And 1.7, if you go to this table, and this is the only thing that we have is this table. And if you go to this table, 1.7, the corresponding value for 1.7 is right here. The corresponding value is 0.9554. But what is this 0.999554? Remember, 0.994 is the area to the left. The table only give you the area to the left, but now they ask you for the area to the right. How do I find the leftover? The total area. To find the item to the right, you need to take 1 minus this answer from the chart. So 1 minus this, you can see that the leftover. Why 1? Because the total area underneath the curve is equal to 1, or 100% if it's in percentage. Okay, so if they ask you to find the area to the right, the one thing that you need to do, one extra step that you need to do, is you need to take 1 minus the percentage that, or the area that they give you in the table. Okay, and if they ask you for the area in between, let's try another one. If they ask you for the area to the right of this item here, how do you find the area to the right of this item? Like I mentioned, the first thing you want to do is you want to sketch. I did not sketch here. I guess I don't have the sketching item I have. But again, area to the right, if you look at this thing here, z-score of 0.95 is right here. And because we try to find the area to the right, we know that in order to find the area to the right, I need to take 1 minus this number, whatever the area is, because the area they give us is only the area to the left. So to find the area to the right, I need to take 1 minus this area to the left. Okay. Yes, we always subtract 1 because the total is always 1. The total, the maximum area that you have is 1. And because they ask us for the right, we need to subtract whatever the left side is. So the area to the left, life is easy. The answer is in your table. If they ask you to find the area to the left of whatever the z is, the answer is in your table. If they ask you for the area to the right, yes, you have to take 1 minus the area, not the z-score. Again, not the z-score. We do not take 1 minus the z-score, ladies and gentlemen. We take 1 minus the area, right? So the z-score of this item right here, the z-score is 3.5, but we subtract the area, right? So the area is 0.3632. So to do this thing here, I need to take 1 minus that, which is the leftover. The item on the right is 0.6368. Okay. So again, that's what we need to do if we need to find the area to the right. Whatever they ask us to find the area to the right, we need to take 1 minus the area to the left, because the table gives you the area to the left. So if you take 1 minus the area to the left, you have the leftover, and the leftover will basically the area to the right. Okay. So those are the first two questions. The first two questions is they will ask you for the area to the left. Area to left, life is easy. The answer is in your table. Whatever the area in here, that is the area to the left, right? Whatever the area in here, that's the area to the left. Area to the right, life is not so much easy. We have to do one operation, which is we take 1 minus the area to the left to give us the area to the right. Now, the last question is, how do we find the area in between? How do we find the area in between? So if you're looking for the area in between, this is what you need to do. And this is what I did earlier, if you are a little bit puzzling about the item. If you find the area in between, this is what you need to do, is you need to take the higher, the bigger area, subtract the smaller area, okay? You need to take the bigger area, higher area, minus the lower or smaller area. So let's take a look at this item. Let's take a look at this item here. This is what they ask you, is find the area between the z-score of negative 1.70 and the z-score of 1.1. So to find this area, this is what you want, or this is what you want to, for me, this is what I sketched them out, right? So I know that the negative number, the smaller number is on the left. The number, smaller number, the negative 1.7 is here, and the 1.1 is here. And again, with the empirical rule, there's nothing you can do with, with this empirical rule, you cannot do it, because empirical rule is only 1, 2, and 3. So now this is what you need to do, is you need to find the area for both z-score. What is the area of the z-score of negative 1.7? Well, negative 1.7 is right here, right? We're looking for the area in between. That's the green shaded item. Negative 1.7 is 0.0446. And that's from the left-hand side to that. And I need to look for the area of 1.10. 1.10 is 0.684. So everybody see those are the two z-score, and the area corresponds to the z-score that I have. But that's not my answer, because I'm not looking for the whole thing. I'm not looking for the whole 0.8643, because that is telling me that from this item, from all the way over here to here, that is 8643. But I'm not looking for the whole thing. I'm only looking for this item. Everybody see that I'm only looking for this box right here. I'm only looking for from here to here. This region right here, if I were to, I'm only looking for this item right here. I don't want the whole thing. I only looking for a portion. So how do I find a portion of the thing? Well, to find a portion, if I know that the whole 9 yards is 0.8643, and the leftover or the small portion that I don't want is 0.0446, do you agree that all I need to do is take the higher number, 0.8643, minus the smaller number, 0.0446. If I minus that, everybody see that in between the two value is 0.8197, right? The leftover is basically, we don't want this group, right? We don't want this item right here. This is the small portion that I don't want because it's not the item I shaded. And if I don't want it, I need to subtract them out. And if I subtract them out, the leftover, the answer is this right here. It's not this answer because this is the whole thing. I just want the middle part, and the middle part is that. Okay. So again, I know this is the first time you saw this thing here. This is the last item we have in chapter 11, ladies and gentlemen. And I know some of you guys probably have a little bit puzzling, and I am